Welcome back to our exploration of signal and systems. In Module 1, we laid down the fundamentals. We learned how to classify signals, how systems behave, and how we can represent signals in both time and frequency domains using tools like convolution, Fourier series, and Fourier transforms. Now, in Module 2, we take these concepts further into the power tools of signal analysis. Here we will introduce the Laplace transform for continuous time system analysis. Use state space formulation for analyzing and designing systems. Understand sampling theory and how to move between continuous and discrete time. Apply the Z-transform for discrete time systems. Discuss practical implementation using MATLAB for signal processing and system analysis. This module shifts us from what signals and systems are into how to work with them at an engineering level. Section 1, Laplace transform for continuous time systems. Why Laplace? The Laplace transform is like a Swiss Army knife for system engineers. While Fourier transforms are great for steady-state sinusoidal analysis, the Laplace transform allows us to handle transients, initial conditions, and unstable systems. Think of it this way. The Laplace transform lets us step into a complex frequency domain, where differentiation and integration become simple multiplication and division. This makes solving linear differential equations almost effortless. Key advantages. Simplifies solving for system outputs. Handles initial conditions naturally. Lets us define transfer functions that describe system behavior completely in the frequency domain. In practice, engineers use Laplace transforms for designing electrical filters, predicting mechanical vibrations, modeling chemical processes, control system design, transfer functions. Once we take the Laplace transform of a system's input-output relationship, we often end up with a transfer function, a ratio describing how input frequencies are modified by the system. Transfer functions are gold in engineering. They give a blueprint of how a system behaves. They can be used to predict stability, frequency response, and resonance points without ever solving the time domain equations directly. Section 2, State variable formulation. What is state space analysis? State space analysis is a way of describing a system using a set of first-order differential equations rather than a single high-order one. The state variables are like the system's memory. They store the essential information needed to describe its future behavior. Why this is powerful? It can handle multiple inputs and multiple outputs, MIMO. It's not limited to time-invariant systems. Time-varying systems can also be analyzed. It's computationally friendly, making it ideal for MATLAB simulation. Practical uses. Modeling robots that have multiple moving parts. Designing flight control systems in aerospace engineering. Simulating electrical circuits with multiple feedback loops. In audio form, you can think of state space as a snapshot system model. You freeze time, write down all the important quantities, and then use equations to predict the next moment. Section 3, Sampling theorem and signal reconstruction. Why sampling matters. Almost every modern signal we work with, audio, video, sensor data, is processed digitally. That means a continuous signal has to be sampled first. The sampling theorem tells us the minimum rate at which we must sample a signal so that we can perfectly reconstruct it later. Key idea. If a signal contains no frequency component above a certain limit, called the Nyquist frequency, then sampling at twice that frequency will capture all the information. Aliasing. If we sample too slowly, something called aliasing occurs. High-frequency components masquerade as low-frequency ones in our sampled data. Aliasing is the reason why wagon wheels in old films appear to spin backward, the sampling artifact from the camera's frame rate. In practice, audio CDs use a sampling rate of 44.1 kHz because human hearing tops out around 20 kHz. Medical imaging machines carefully choose sampling rates to avoid false readings. Section 4, Z-transform for discrete time systems. Why the Z-transform? Just as the Laplace transform is used for continuous time systems, the Z-transform is the tool for analyzing discrete time systems. Key points. Convert sequences into a domain where difference equations become algebraic equations. Makes it easy to find system responses, stability conditions, and frequency characteristics. The transfer function in the Z-domain tells us how a digital system modifies different frequency components, essential for designing digital filters. Applications: speech signal processing, image enhancement algorithms, noise reduction in communications, DSP-based control systems. Section 5, MATLAB for signal processing and system analysis. MATLAB is not just a calculator, it's an engineering laboratory in software. In the context of signals and systems, MATLAB can generate and visualize signals, perform convolution, Fourier transforms, Laplace transforms, and Z-transforms, simulate system responses to different inputs, plot frequency responses, Poisson diagrams, and time domain outputs. For example, you can create a synthetic sine wave, filter it, add noise, and analyze the result, all in a few lines of code. You can test a control system stability before physically building it. You can prototype a digital filter for audio processing. MATLAB also has specialized toolboxes, like the Signal Processing Toolbox and Control System Toolbox, that make it even easier to implement the theory we've covered. Section 6, Integrating the concepts. By now, you should see how all these tools connect. We represent signals and systems in time and frequency. We analyze continuous time systems with Laplace transforms and transfer functions. We model complex systems with state variables. We digitize signals with sampling and protect them from aliasing. We solve discrete time systems with Z-transforms. We implement everything in MATLAB for real-world applications. This is not just academic, this concept drive telecommunications infrastructure, multimedia streaming, industrial automation, medical diagnostic equipment, spacecraft navigation systems. Section 7, Summary of Module 2. In this module, we have explored Laplace transforms and transfer functions for continuous systems, learned the state space method for handling complex, multivariable systems, understood the sampling theorem and the importance of avoiding aliasing, applied the Z-transform for digital signal analysis, integrated all these tools using MATLAB. With both modules complete, you now have a strong foundation to analyze, design, and implement systems that handle signals in almost any engineering context. The next step is practice. Apply these methods to real-world problems. Use MATLAB to simulate, test, and refine your understanding. The best engineers are those who can move seamlessly between theory and practical implementation.